right, so with the last section of this solutions chapter, we're going to start to look at concentration. And specifically, we're going to look at the concentration unit known as molarity. And then with these or with this one concentration unit, there are a whole bunch of other ones. So there's percent by volume, percent by mass. So there's a couple other things. But we're going to focus on molarity. But the reason concentration is going to be important is it's going to tell us how much of that stuff we actually have dissolved in solution. So if we think about something like an acid or a base, essentially just looks like water. It's just a colorless liquid. So we can't just visually inspect it and know how strong that acid or the base is going to be. But the molarity is going to give us that information. And if we think again about acids and bases, if we've got a concentrated acid, so where we have a lot of that substance dissolved, we're going to need to handle it with a lot more caution than we would with a very dilute acid. So something that only has a little bit dissolved in there. Sorry, I got interrupted for a second, so I forgot where I paused this video and what I was saying. But with this molarity, it's just going to be important because it's going to let us know how much of that substance is dissolved in solution. So remember, with solutions, we've got two pieces, the solute, so the substance that's getting dissolved. So in a sulfuric acid solution, for instance, the sulfuric acid would be the solute, and then the solvent is going to be the substance that does the dissolving. So typically it's going to be water. And with this molarity, we just have to make sure that we've got the correct pieces there. So we've got moles of solute and volume of solution, but we have that in liters. So the big thing is just to make sure we have those units correct. So we need to have moles and we need to have liters, because what we'll see quite often, especially since when we're working in the lab, we're typically working with relatively small quantities. So a lot of the times we're going to have milliliters for the volume. And then also when we're weighing something out, we can't weigh moles directly. We can only weigh the grams. So in some cases, we're going to have to do a little bit of a conversion. And for the one we're looking at here, we're told how much of the sodium sulfate dissolves in grams, and then we're told how much of that solution is made in terms of milliliters. So we have to convert both of those units with this one. And if we wanted to, we could do each of those conversions separately. So you could go grams to moles using the molar mass, and then we could divide milliliters by 1,000, just move that decimal over 3. Or we can do that all in one step. And then for this, we need to know what the formula of sodium sulfate is going to be. So Na2SO4, since sulfate is going to be -2, sodium is going to be +1. So we'll need 2 of those sodiums to balance out the sulfate. And then that's going to have a molar mass of 142.05 grams per mole. So like I was saying, we can do this in just one string of calculations just using dimensional analysis. So we can do grams on top. We can do milliliters of solution on the bottom. And then just like we would normally do, we can just set up our dimensional analysis, focus on each of those units separately, and just make the necessary conversions. So for the top piece, in order to get that from grams to moles, we're just going to use that molar mass. So we'll plug in grams on the bottom, so grams cancels. And then that'll leave us with moles on top, just the unit we want. And then the same thing with the volume. It's just in this case, we've got milliliters on the bottom. So in order to cancel that, we need to put milliliters on the top. And we'll just have 1 liter on the bottom there. So when we go through and actually plug this one in, what we're going to see is that'll have a molarity of 1.32 molar. So the way we would describe molarity is just with molar. So in this case, it'd be 1.32 molar solution of sodium sulfate. But the capital M is just going to represent the molarity there. And with it, like I said, the big thing is just making sure we do have the correct units. If we have grams, we just need to do the molar mass conversion to get to moles. And then with the volume, we don't really even need to do that dimensional analysis if we can just recognize that milliliters to liters is going to be a change of a factor of 3. So we can just move that decimal over 3 if we wanted to. So we could really kind of simplify this just that one step if we initially just put in 0.125 milliliters there. All right. And then with the second one, now we know the concentration of the solution. We want to identify what ions we're going to have. or what the concentration of those ions are going to be. So we still need to figure out what that formula is going to be. And what we're going to see is calcium will be +2. And actually, let me do it like this. So calcium will be 2 plus. Nitrate is going to be NO3 minus. So when we do the crisscross method, what we're going to see with the formula there is we'll need 2 of those nitrates to balance out the calcium. And then if we actually take calcium nitrate, Ca, and then in parentheses NO3 2, and dissolve it in water, since it's a soluble ionic compound, it's going to completely dissociate. So we're going to get 1 of those calcium ions, and we're going to get 2 nitrate ions. So now if we think about what this concentration is going to be, the calcium nitrate has a concentration of 0.025 molar. And for every 1 of these calcium nitrate molecules, we're going to wind up getting 1 calcium ion. So what we're going to see is the calcium ion concentration is going to be exactly the same. But with the nitrate, now we're getting 2 of those nitrate ions for every 1 calcium. So what we could do is basically set it up like this: 0.025 moles of calcium nitrate for every liter of solution. Because again, that capital M just is moles per liter, so we can actually break that capital M into moles and liters separately, like we have here. And then just looking at the equation, for every 1 mole of calcium nitrate, we're going to get 2 moles of that nitrate ion. So what we're going to see is the concentration of that nitrate ion is actually going to be twice the concentration of the calcium nitrate as a whole. And it's going to be because, again, we get 2 of those nitrate ions for every 1 molecule. So we actually have twice as many moles of nitrate as we do calcium or calcium nitrate. And then with this, we can use this to determine or allow us to figure out how we're going to make a solution. And we're going to see 2 different ways we can make that solution. One of them is going to be by taking the solid solute and dissolving it in water or whatever that solvent's going to be. And the other one we'll see is just using a already prepared solution to make a more dilute one. But when we're making a solution from the solid, we're going to, like I mentioned before, we're going to need to know the mass of that solute that we want in order to get the actual concentration that we're interested in. Because the balance, like they're shown here, doesn't read in moles. We can only measure grams directly, so we have to get the grams of that one. But when we're actually making the solution, the way that this process is going to occur is we'll figure out how much of that solute we need for a solution with the given concentration and the desired volume. So we'll do all of our calculations beforehand, figure out how much of that solute we need. And then when we go to make it, we're going to add the solute to our volumetric flask first. So on the right-hand side, we've got a volumetric flask. And with it, you can't see it here, but there's just going to be a mark on that flask somewhere on the neck of it. So I just put a red line randomly there. But with these volumetric flasks, they're going to be very accurate for just that one volume. So if we can get the solution right on that mark, we're going to have the exact volume for whatever that volumetric flask is. So it could be 100 milliliters, could be 250, could be 10. But whatever the flask is designed for, it's going to have that specific volume measured. But if we go above or below that mark, we can't be certain how much we actually have in there. So with this, the reason we're going to add our solute first is because if we add our water to the flask first, and we get it all the way up to that mark, and then we go to add our solute, that solute itself is going to have volume. So we're going to wind up going above that mark. We're going to have a little bit larger volume than we intended, which means the concentration is just going to be a little bit below what we wanted as well. So when we're making a solution from a solid, we'll always add the solute first, and then we'll add the solvent up until we hit that point on the volumetric flask. So that's why it's often said when you're making a solution, and we may have had it on the previous one. Yeah, so in this case, they don't say we add 125 milliliters of water. they say add enough water to form 125 milliliters of solution, because the 23.4 grams of sodium sulfate is also going to have some volume. So if we added exactly 125 milliliters of water, now our solution is going to be larger than that volume, just because it's also going to have the sodium sulfate mixed in there. But if we look at the question here, how many grams of sodium sulfate are required to make 0.350 liters of 0.5 molar sodium sulfate? With this one, we could use that molarity equation. So molarity is equal to mole over liter. And in this case, we have the molarity, we have the liters, so we could cross multiply and figure out how many moles that is. And then we could use the molar mass to convert. So with this one, it's the same substance we looked at in that first question. So it's going to be 142.05 grams per mole. But we, again, can use this, we can use dimensional analysis just to do this in one string of calculations. And the reason we're going to be able to do that is because that capital M molarity can be split into moles per liter. So if we start this one, we can start with the volume of that solution we need, 0.350 liters of solution. And then we're told we want to make 0.500 molar solution. So what that 0.500 molar really is really half a mole for every liter of solution. So now if we look at our dimensional analysis, we're starting with liters. We have to get to moles so then we can get to grams. So we can just use that molarity. But we can use that molarity to convert directly between volume and moles. And then we can use the molar mass just to get the actual mass that we would need to weigh out in order to make that solution. So I don't know why this keeps happening so much, but it's really getting annoying. But let me just fire that slide quick. So in this case, 0.350 liters. And then again, we can use split molarity into moles per liter rather than the capital M. So if we stop at this point, this is telling us how many moles of that sodium sulfate we would need in order to make the desired solution with the desired volume. But we can't measure out moles, so we need to go one step further. And again, this is just the same molar mass as we saw with sodium sulfate before. So just adding up one sodium, or two sodium, excuse me, one sulfur, and those 4 oxygens. And when we go through and actually do this calculation, what we're going to see is we'll need just a little under 25 grams of that substance. And then, as I mentioned, we can make the solution from the solid, or we're going to be able to also use a previously made solution to make a more dilute one. So concentrated means we're going to have a lot of that solute, whereas dilute means we're going to have less of it. So we can use a higher concentration solution to make a lower concentration one. And it's going to work in a similar way. It's just instead of starting with the solid, what we're going to do is initially transfer some of that original solution into a separate flask, and then we'll just add enough water to, again, bring it up to the line on the neck of the flask. So what you're looking at on the picture at the bottom here, that could be a copper solution or whatever it's going to be. I'm just saying copper because it's blue. But we're going to take some of that initial solution, transfer it to the second one. And at this point, those 2 flasks, I don't know why I circled the one on the left as well, but with the middle picture there, with this picture, at that point, since all we've done is transfer one solution to or part of one solution to a second flask, at this point, the concentration of both of those flasks is going to be the same, because we've moved some amount of moles, but we've also moved some volume with the solution as well. And those are going to be related just because, remember, solutions are going to be homogeneous, meaning that they're evenly mixed. So when we go to transfer the solution, we're not picking one part of that initial solution that's high concentration and leaving behind a low concentration. It's even throughout. So if we just kind of split it between 2 beakers even, we still have the same solution, in terms of concentration. We just have half as much in each of those beakers. It's a similar idea here. Now we're just transferring some of that initial higher concentration solution to a second flask. And then with the picture on the right, what we're seeing there is after we then add the water, we bring that second solution up to the mark on the flask. What we're seeing is now a lighter color, because this is going to be a lower concentration. It's going to be more dilute. So if this is a copper solution, for instance, we still have some of that copper dissolved. That's why we still have that blue color. But now that we've diluted it, we've added more water. We've got a lower concentration, and that's why the blue color just starts to fade a little bit. And then with this process, what we're showing here is just one dilution. What can also happen, and a lot of the times if you're working in a chemistry lab, you'll do what's known as a serial dilution. So serial just meaning sort of repeated. I guess I should have wrote it on the other side of dilution so it actually made sense. But with the serial dilutions, now we're just going to kind of repeat that process. So if we were to do a serial dilution, what we would do is then just take this new solution and repeat that same process. So we'd make an even lower concentration, and then again, a lower concentration still. So if we were to repeat this process over and over, we would just see that blue color get lighter and lighter each time. Just because we're going to have a more dilute solution, we're going to have a lower concentration there. So we'll have less of that solute actually dissolved in each subsequent solution. And with this, we don't want to just go randomly taking some amount of the initial one and then adding some amount of water to the solution. We've got an equation that actually allows us to calculate how much we're going to need. So when we're looking at the equation here, sometimes you'll also see a very similar equation where it's just M1V1 is equal to M2V2. And it means the same thing with the one on the left, the original one here, MCVC is equal to MDVD. What this is representing is just the molarity and the volume, and then C and D, or 1 and 2, are just referring to the initial higher concentration concentrated solution. And then D is referring to just the lower concentrated, the more dilute one. So if we were actually to do this in a lab or something, we would know the desired concentration of the solution we need to make. We would know how much of it we need to make. So we would know the right-hand side. And then we would also know the concentration of the solution we're going to use to prepare this new one. So what we would be solving for is VC. We're determining how much of that initial solution do we need to transfer before we dilute it up to the mark with the rest of that solvent. And then with it, that would be what we're doing in a lab. But we can use this equation to solve for any of those variables, provided that we have the other three. So if we look at a question here, how many milliliters of a 3 molar sulfuric acid solution are needed to make 450 milliliters of a 0.1 molar solution? So what we're looking at here is MC, that initial concentration, VC, oh, that'll be VD, and then MD. So when we go to plug this in, we'll have 3 molar, and we're solving for VC. We're trying to determine how much of that concentrated solution do we need to transfer in order to make the dilute one. And then with the dilute one, we'll have 0.1 molar, and then a volume of 450 milliliters. With this equation, it doesn't actually matter what the units are on volume. So with molarity, we need moles over liters. But in this case, since we've got the same thing on both sides, the units themselves are going to cancel. We just need them to match. So if we've got milliliters on one side of our reaction here, or equation here, excuse me, we're going to need milliliters on the other. Or if we have liters, we need that on both sides. So in this case, since we're given milliliters, and that's what we're trying to solve for with the other volume, I would just keep it in milliliters. Save yourself the hassle of converting it to liters and then converting that answer back to milliliters. But when we go through and solve for this one, we'll divide each side by 3 molar. So that'll cancel. 3 molar on this side. We'll see that the units there cancel. And that's why we're going to be left with just milliliters, because that's what our volume unit is on that side. So what we'll see is we would need to transfer 15 milliliters of that concentrated solution. and then dilute it with water all the way up to 450 milliliters total. And that would give us the desired 0.1 molar sulfuric acid solution that we're trying to make there. And then with this, we've already kind of seen it a little bit. So we've actually seen this piece in chapter 3 when we were just doing those gram to gram conversions. So remember, we have to relate one substance to another using moles. So if we started with grams of A, we could use the molar mass of A to get moles, use the chemical reaction, those coefficients to go from moles of A to moles of B, and then do the same thing with the molar mass of B just to get to grams there. What we're going to be looking at with these solutions is going to be similar, but rather than using molar mass, what we're going to be able to do is use the molarity to either go from moles to volume or from moles to molarity, depending on which direction we're trying to go there. But again, we're going to be taking advantage of the fact that capital M is really just moles per liter, similar to how the molar mass is grams per mole. So if we're given the volume, we can use the molarity as it is, moles over liter, just to convert to moles. Or if we're given the moles, we can use the molarity just inverted, so we'd have moles on the bottom, liters on top, to determine what the volume is going to be there. And if we look at the question here, we're going to actually need to get the reaction for this one. So how many grams of calcium hydroxide are needed to neutralize 25 milliliters of nitric acid? And remember, with acid-base reactions, these neutralization reactions, we're always going to produce water and then some salt. So in this case, we'll have H2O. And then since we have calcium hydroxide and sodium nitrate, or nitric acid, excuse me, we're going to wind up creating calcium nitrate. So when we go to balance it, we'll need 2 of those nitric acid molecules for every 1 calcium hydroxide. And then that'll also give us 2 water molecules for every 1 calcium nitrate. But now that we have our chemical reaction, we can use that stoichiometry. And we're trying to get to grams. So the second half of this dimensional analysis is going to be the same as we did in chapter 3 with the gram to gram conversions. But in this case, we're not starting with some mass of that nitric acid. We're told we have a volume and a molarity. So what we can do, and I'm just going to immediately divide this by 1,000 just to save myself one step. But 25 milliliters is just going to be 0.0250 liters. So we can use the molarity. So liters HNO3. And then that molarity, 0.1 molar, really just means we'll have 0.1 mole for every liter of this solution. So if we stop at this point, that tells us how many moles of nitric acid we would have in this volume of that particular solution. And now that we're in moles, we can use the balanced chemical equation to go from nitric acid to calcium hydroxide. And then the final step here, just like the previous chapter, we can use that molar mass to go from moles to grams. So we'll have moles on the bottom. And then with calcium hydroxide, we're going to see the molar mass is just a touch over 74. And if we look at it, liters canceled, moles of nitric acid canceled, moles of calcium hydroxide cancel, and we're just left with grams of that substance. So if we actually go through and do the calculation, what we're going to see is we should get 0.0926 grams. And then again, that's going to be of the calcium hydroxide. So CaOH in parentheses and 2. And then with these reactions in solution, sometimes we're going to see what's known as a titration. And this is going to be an analytical technique where we can use a known solution to determine the concentration of an unknown. So a lot of the times, or at least sometimes we'll see a formula like this. Because with those molarities, and actually, yeah, with the molarities, again, mole per liter. So if we multiply it by volume, we'll get moles. So the moles of A is going to be equal to moles of B. So if we think about an acid-base reaction, we could think about hydrogen ions and hydroxide ions. That neutralization is going to occur when we've got equal moles of acid and base. And with these titrations, what we're going to be doing is using a known solution. So in the we've got two different solutions here. If you look, we've got the burette, which is the glass tube, and then we've got the flask. And with it, we'll know the volumes of both of these, because with the flask, we measure out exactly how much we put in there initially. And then with the burette, there's actually graduations on there. So similar to a graduated cylinder, we can measure the initial volume, we can measure the final volume, and then just do the difference there to get the overall. So we can get both of these volumes just based on how we set this experiment up. And then how much of the other substance we use. And then we'll know the molarity of one of them, just because we'll prepare that solution ourselves. So the unknown is going to be the one that we're solving for. And typically with these titrations, there's going to be some sort of color change involved. So with an acid-base reaction, acids and bases are going to be colorless. So if we react them, we're not really going to see anything occur. So what you're looking at in the picture here is going to be known what's known as phenolphthalein, just a pH indicator. So once we reach the endpoint, is what it's known as, where we see that color change, that's just telling us we've kind of reached the spot in our reaction that we wanted to get to. That's going to be, if we choose the correct indicator, that's going to be where we have equal moles of acid and base, or whatever the reaction is going to be for. We'll see it in lab with acids and bases, but you can do it with other types of reactions like we see here. So in the case of this reaction, the quantity of chloride ions in municipal water is determined by titrating the sample with silver ions. So remember, silver chloride is going to be solid, so we're going to form a precipitate in this case. And then the endpoint of the reaction shown is marked by a color change, so we're still going to use an indicator so we know when that endpoint is reached. And we're asked how many grams of chloride ions are in a sample of water if 20.2 milliliters of 0.1 molar is needed to react with all of the chloride ions. And with it, we're not actually going to be using the MA-VA equation here. We're still going to be doing dimensional analysis, but we're going to be doing it in the context of a titration. So if we look at it, we're given, the volume and the concentration of the silver solution that's used. We want to determine how much of that chloride was then present. So how many grams of it were present if we had that much silver used. So we'll be able to go through the dimensional analysis just like we did in the previous one. But with this one, I'm just going to have to go to the next slide just because there's not a lot of room here. So I would encourage you to try to work through this one on your own. And you may want to pause the video just so you can see all the information. But with it, just note that it's a 1-to-1 mole ratio with all of these substances. So 1 mole of silver ions plus 1 mole of chloride ions gives us just 1 mole of the silver chloride precipitate. So when we look at this one, what we're going to see is we'll start with that volume. And again, I'm going to convert it directly to liters immediately, excuse me. So 20.2 milliliters is really just 0.0202 liters. And we can use the molarity of that silver solution, just split it into moles and liters. So 0.1 molar is just 0.1 mole per liter silver ions. And then 1 mole silver ion, according to that reaction, will be equal or equivalent to 1 mole of the chloride ions, which are going to have a molar mass of just about 35.5. So when we go through and actually plug this in, what we're going to see is that in that sample, there's going to be 0.0709 grams of those chloride ions. And then it also asked what percentage of that solution is going to be chloride ions if the sample of the sample had a mass of 10 grams total. So what we'll be able to do then is just take that, take the amount of chloride we had, just a percentage is always just part over whole. So in this case, we're focused on the chloride ions in the larger sample, 10 grams. And then to make it a percent, we'll just multiply by 100. So what we'll see here is we'll wind up with a percentage of 0.709, excuse me. And then we'll have a percent there just because the grams are going to cancel in the numerator and the denominator. So with the percentage, we always just have the percent. And then with the next one, I think we've got 2 more, 3 more. Oops. 57, 3 more. So with this one commercial method used to peel potatoes is to soak them in a solution of sodium hydroxide for a short time, remove them from the sodium hydroxide and spray off the peel. And the concentration of sodium hydroxide is normally in the range of 3 to 6 molar. And they periodically analyze the sodium hydroxide. In one such analysis, 45.7 milliliters of a half molar solution of sulfuric acid is required to neutralize 20 milliliters of that sodium hydroxide. What is the concentration? So again, we need to have the equation here. And what we're going to see is for every mole of sodium hydroxide, or for every mole of sulfuric acid, rather, we'll have 2 moles of sodium hydroxide. That'll give us 2 moles of water plus 1 mole of sodium sulfate. And now that we have the equation, we can do the dimensional analysis just like we did. Again, I'm always just going to convert that volume just to liters initially, so I'm just going to move that decimal over 3. But we could do 45.7 milliliters to start, and then just have our first conversion from milliliters to liters. But just to save us a step, I'm just going to do that in 1. And now that we have the volume in liters, we can use the molarity of that solution. So we're looking at the sulfuric acid to start. For every 1 liter of that solution, we're going to have 0.5 moles. Again, sulfuric acid to start. And what I'll do is actually just underline these so we can see what information is going to what. And then with the reaction, 1 mole of H2SO4 is going to be equal to 2 moles of NaOH. And then what we'll have now is the moles of sodium hydroxide, which if we solve for, is going to be 0.0457, which makes sense because we had in those parentheses half and then 2. So the number itself isn't actually going to change. But instead of liters, now we're looking at moles. But if we want to ultimately get the concentration of that sodium hydroxide, we'll then divide it by the volume. So we'll take the number of moles we have there, divide it by, we want to again change this to liters. And there really should be another 0 there at the bottom just because the original volume is 20.0 milliliters. So we really should have 0.0200 liters. And now when we do the division here, what we're going to see is the concentration is then going to be 2.29 molar. So with these, the big thing is just recognizing we can use that molarity as a conversion factor itself, because it's going to link moles and liters for whatever that solution is. And then once we're in moles, we can use the balanced chemical equation just to relate one substance to another using those coefficients. All right. And then we got this one, and then just one other one we'll look at in this video. but we're told in this case a sample of iron ore is dissolved in acid and the iron is converted to iron 2+. The sample is then titrated with 47.2 milliliters of a 0.0224 molar MnO4- solution. The oxidation reduction reaction is shown below. Looks like a pretty complicated reaction. But when we look at the questions, if we just take it step by step, we'll see it's not really going to be too much different than what we've been looking at so far. And with the first question, we want to figure out of that permanganate, MnO4-, how much or how many moles were added to the solution. And with it, we can do that just with the information here. So we have the molarity, we have the volume. We can convert that to liters. So we'll have 0.04720 liters. And then we can put that over a liter. And then for every 1 liter, we'll have 0.0240. Oops, let's get bad writing. So I'm struggling to squeeze this into the bottom here. I should have gone on to the next slide. But what we're going to see is that'll give us a very small amount of moles, 0.001057. And that's going to be for the moles of that permanganate. So with the second piece, how many moles of Fe2+ were in the sample? Now we can use the stoichiometric coefficients from the balanced reaction just to relate these to one another. So with the iron, we would just be able to multiply this by 5, because for every 1 MnO4-, we're going to get 5, or we're going to need 5 of those iron ions. So we would just multiply that by 5, and for B, what we would see is 0.005286 molar. This will be MnO4-. All right. And then with C, we've already done this before as well. How many moles of how many grams of iron were in the sample? Excuse me. We can use the molar mass, so we can just multiply 0.005286 moles by 55.85 grams per mole, because the moles are going to cancel, and we'll see when we do that, C is going to be 0.2952 grams. And then with D, we can just take that amount and divide it by the total mass, so 0.8890, and multiply it by 100 to get a percentage. And what we'll see there is 33.21%. So with it, we've got C is equal to that, D is equal there, B is equal to that, and then we've got A at the bottom here. So it's kind of a weird way to go through it, but if we just take it by step by step, it's not anything that we haven't seen before. So again, we can get the moles just using the molarity as a conversion factor. So since we have the volume, you could also use the molarity equation. It would ultimately be doing the same thing, because we would just be cross-multiplying the molarity times that volume. And that's exactly what we're doing with the dimensional analysis at the bottom. So we can get the moles of permanganate. Then we can use the equation to relate that to moles of iron, and then use the molar mass to get the grams of iron, and then just do part over whole to get the percentage of iron in that ore sample. Right. And then with the final one here, what is the molarity of a sodium what is the molarity of a sodium hydroxide solution if 48 milliliters is needed to neutralize 35.0 milliliters of 0.144 molar sulfuric acid? So we've actually seen this reaction before. We've written it at least once. So what we're going to see is 2 moles of sodium hydroxide plus 1 mole of sulfuric acid gives us 2H2O, and then just that sodium sulfate, which would be soluble. So if we wrote the net ionic equation, we would just remove sodium and sulfate from both sides of the reaction. We'd ultimately just see it's hydrogen ions plus hydroxide ions, giving us that water. And just like the previous ones, oops, we should have 0.0350 liters there. And then we can use the molarity. So 1 liter will have 0.144 moles of that solution in it. And then that was describing the sulfuric acid. So for every 2 moles H2SO4, we need 1 mole sodium hydroxide, NaOH. And then with the final step here, and write this one down so I don't actually have to get the answer. And I went one too many parentheses. But with this one, this is going to give us moles of sodium hydroxide, and I need to actually calculate what that's going to be. 0.035 times 0.144 divided by 2. And we get 0.00252. And that's going to be moles of sodium hydroxide. We have the volume of it. So what we can then do is just take 0.00252 moles divided by 48 milliliters, but we'll want to convert it to liters first. So we'll have 0.0480 liters. And then what we'll see there is divided by 0.048. And with this, you can always kind of double check just to make sure if it seems reasonable at all. Because with this, we've got a larger concentration of sodium hydroxide, or a larger volume of sodium hydroxide. So it makes sense that the concentration is going to be a little bit lower there. And essentially, we have 2 moles of sodium hydroxide per every 1 mole of sulfuric acid. So if we really double that concentration, that'll give us a better relationship with the concentration of sulfuric acid. So doubling 0.0525 would just give us 0.15 or 0.105, excuse me, which is still lower than the sulfuric acid, which makes sense because we've got more of that sodium hydroxide solution. So with these ones, always just kind of double check, make sure if the numbers seem reasonable at all, just because it would be easy to either put the molarity, just set that up wrong. So we could have that first dimensional analysis step flipped, and in which case we're going to get a much larger number. Or if we have the volume on the bottom in milliliters, just going to give us a weird answer. So always just kind of think about whatever answer you get, think if it makes sense in the context of that specific question. But with this is where we'll wrap up chapter 4, and then just remember there is practice problems on the Canvas page. So if you want to go through any more, you can practice with those ones, or if you need additional practice, let me know, or if you have any questions as you go through any of that, let me know as well.